All right, so today you are going to be answering the question, how do we graph a derivative? What you're going to want to know is that the slope at a point on f of x becomes the y value on f prime of x. So let's take a look at this first example here. We have what looks like a quadratic because it's a parabola. If you look at point A and draw in just a little tangent line there, that's what I drew in green there, you will see that at point A your slope is negative, and we're going to say it's probably about -1. Okay, so we put a point, the slope on f of x becomes a point on f prime of x on your derivative. Okay, so that point is right here. Then let's look at 0. At 0, our slope looks about horizontal. If you look at that little tangent line I drew there. Since the slope there is about 0 on f prime of x, we're going to graph a point at 0. And here at point B, we can see that slope. It's about the positive version of the slope we found over here at point A. So we'll say that that's about +2. So as you can see here, these 3 points show us that this derivative graph is a straight line. All right, so now let's look what happens when our original function is a straight line. Now remember, derivative is slope. So if we look at point 8 here, the slope there is, well, we can figure it out, right? Because this is a straight line the whole way. The slope there is -1. So on f prime of x, we put a point at -1. At 0, it's a straight line. The slope of our tangent line is still going to be -1. And at point B here, since it's a straight line, our slope is still -1. So as you can see, the graph of our derivative is a horizontal line through -1. Because remember, derivative represents slope. The slope is always -1 of this line, so our derivative will always be -1. Now if we go on to a trigonometric function, this actually represents sine of x. So we're going to look at these points that are given on the graph here, A, B, C, and this one is supposed to be D. Okay. At A, we look here and we estimate that slope is probably about 1. So at A, we go down to our derivative graph and we estimate that that is about 1. So we'll go right up here. That's where 1 is. Now at point B, that looks like a horizontal tangent line, so the slope there is 0. So we go down to our derivative graph and put a 0 there. Then we go here to point C, and we can see that our slope there is about -1. So then we go down to -1 on our derivative graph. Then at point D, again, we see we have a horizontal tangent line. So our slope there is 0, so down on our derivative graph we go to 0. So as you can see here, our graph looks something like that. Now, if you were to continue to draw this graph, what does the derivative of sine of x look like? This is sine of x, this is the derivative. If you thought it looks like cosine of x, you would be correct. And that actually brings us to Theorem 2.6. Derivatives of sine and cosine functions. The derivative of sine is cosine. We saw that up here by drawing the graph. And the derivative of cosine, if we were to draw that, would actually be negative sine of x. So if we know this is the graph of cosine, if you were to draw the derivative of this graph, you would see then that the derivative of that would be negative sine x. Right, so make sure you get those two memorized. They'll be very important. All right, with this in mind, I want you to pause here and I want you to try and do the next graph on your notes sheet. So take a minute to do that and then we will go on. All right, so if you went ahead and did this graph, you will hopefully see something like this. All right, so here's f of x. Now, as you can see, at 0, our original graph has a vertical tangent line. So our slope there is undefined. So as you can see here towards 0, our derivative is going up to infinity. Then as we go along, our slope appears to be approaching 0. It gets flatter and flatter and flatter. So these points on our derivative graph here are estimates, but they go from being steep to flat, so we're approaching 0, the x-axis. So the derivative of a square root graph looks something like this. Undefined over here towards 0 in this case, and approaches 0 as it flattens out towards infinity. All right, so that's a little bit about how we can graph derivatives. We're going to look next at what else we can do with them besides finding slope at a point and then graphing them. Since slope represents rate of change, we can use derivative for many things: population growth rates, velocity, production rates. And I want you to think about if there's anything else you can represent with a derivative, or what else is represented by a rate. So pause here for a second and see if you can think of one or two more. Today, the one we're going to look at, the example we are going to look at, is velocity. So we're going to be considering motion of an object moving in a straight line along either the x or y axis, so horizontally or vertically. Movement to the right or up is positive. Movement to the left or down is negative. We're usually given a position function. We'll go over what our position functions will be today. And our position functions give position relative to the origin. Two ideas that will be very important to us are average velocity over a certain interval and instantaneous velocity. Average velocity over an interval is going to be change in position, because remember S represents the position function, over change in time. It's kind of like your change in Y over change in X, except for position and time are our variables now. So if we're going over the interval A to B, your average velocity is basically just slope between those points. So the position at B minus the position at A all over B minus A. And B and A will be time in seconds usually. So that's average velocity. If you are asked to find instantaneous velocity, that's going to be a rate of change, because velocity is a rate of change at a particular time. So that's when we have to use the derivative. So the limit as change in time in this case approaches 0 of our average velocity. So S of B minus S of A over B minus A. Now, since this is the limit of a rate, this is really just the derivative of your position. So what you are finding to get velocity is the first derivative of your position function. So you don't have to do the limit when you're finding velocity function. You just have to know your position function and find the derivative of that. All right. For position and velocity today, remember, velocity can be 0, positive, or negative. Okay, so 0, not moving, positive, moving forward or up, negative, moving right or down, left or down. Speed is the absolute value of velocity because it cannot be negative. Just something to keep in mind. Now we have a special free fall formula that we are going to be using, and that is called Newton's free fall formula. Newton's free fall formula is represented by this function. G represents the acceleration due to gravity, which can be two different units, 32 feet per second squared or 9.8 meters per second squared. So just pay attention to the problem you're doing, and that will tell you what your gravity constant is going to be. V sub 0 is your initial velocity. So we're going to be looking at, was the object dropped? A 0 initial velocity? Was it thrown up? You'll be given some sort of initial velocity, so it would be positive, or thrown down, a negative initial velocity. And then S sub 0 represents the initial position. Let's get into an example then. All right, so next we are going to look at this example. At time t equals 0, a diver jumps from a platform diving board that is 32 feet above the water with an initial velocity of 16 feet per second. Here is our position function. Let's find our position and velocity functions for that diver. So since we're talking about feet, we're going to use the gravity constant of 32 feet per second squared. So your position function, S of t, will be negative 1/2 times 32 t squared plus initial velocity. They jump up with an initial velocity of 16 feet per second, so 16t, plus our initial position is 32 because they are 32 feet above the water. So simplify that. Negative 16t squared plus 16t plus 32. Now we need to find a velocity function. Remember, velocity is the first derivative of position. So thinking back to what we did yesterday with velocity, or with derivatives, first derivative of position is velocity. So the first derivative of this function right here, negative 16 times the derivative of t squared, which is just 2t, plus 16 times 1t to the 0, plus the derivative of 32, which is 0. So your velocity function is negative 32t plus 16.